Hello chemistry students, in this video I'm going to give you an introduction to acids and bases. Alright, so start off with this question: what do lemon juice, lime juice, sauerkraut, vinegar, and sour cream all have in common? Well, they're acids. Okay, and not all acids are edible like the ones listed there, but let's look at some properties. So all acids are sour, although I would not recommend tasting all of them. They're electrolytes, meaning they conduct electricity in solution to some degree or another. There are some indicators we use for acids and bases, and acids will change the color of those. Litmus paper is one of those, and litmus paper will change from blue to red in the presence of an acid. It's one of the ways to test for it in the lab. Phenolphthalein is another color change indicator, and it is colorless in an acid. So you drip phenolphthalein, it's clear into an acid, the acid stays clear. Okay, acids will react with metals to produce hydrogen, and they will react with bases to produce water and salt, like you might be able to see on your reference table. Bases, on the other hand, have a bitter taste. They're slippery. That's one of the ways I used to know if I had sodium hydroxide on my hands when I went to wash my hands, or usually gloves when I was in the lab. Bases are also electrolytes. They conduct electricity in solution. Now, the color change indicators are different here, because bases will make red litmus paper turn blue. Now, if you get questions about blue litmus paper, well, blue litmus paper will stay blue in a base, it'll stay blue in a neutral solution, it'll turn red in an acid. Red litmus paper will stay red in an acid, red in neutral or pure water, and it will turn blue in a base. Anyways, phenolphthalein, the color change indicator that was clear by itself and clear in an acid, when that transition happens to become a base, then the solution will turn a bright pink color. I had a beaker that wasn't washed well one time, and they put a base in it, and they're like, why did it all turn pink? And it was because somebody had left phenolphthalein in the beaker previously. Alright, bases react with acids. That's a neutralization, special type of double replacement, to form water and a salt. An example of a base is soap. Most of the soaps we use are just mildly acidic. Another word for base is alkaline, like the alkaline earth metals or the alkali metals. When they combine with hydroxides, they become bases. Alright, when you name acids, binary acids are easy. Those are acids with two elements, one of which will be hydrogen. So it'll be hydro, fill in the name of the element, maybe take off some of the ending, replace the ending with ic. So examples here: HCl, hydrochloric; H2S, hydrosulfuric. Ternary acids are the ones that are formed from polyatomic ions, so they have three or more elements, and some examples there. You should already know how to name these from Unit 4, but anyways, sulfuric acid and chloric acid. And remember that the polyatomic ion, if it ends in 8, then the acid will end in ic, and if the polyatomic ion ends in ite, then the acid will end in us, O-U-S. Alright, so when you name bases, those are named as ionic compounds. So this should be a review from Unit 4 for you. Write the name of the positive ion and then put hydroxide on the end. Sodium hydroxide, ammonium hydroxide, and calcium hydroxide, and so on and so forth. Alright, let's take a look at the different theories of acids and bases. Each one has its own reasons why it might be used, and things that are convenient and not convenient. Anyways, let's look at Arrhenius first. So it is the oldest definition of acids and bases, and it defines an acid as being a compound that contains hydrogen that ionizes to make hydronium or hydrogen ions. Sometimes you'll see this written H plus instead of H3O+. I'll try and talk more about that a little bit later. All right. Typically, that's going to be your acids that begin with H, like HCl, HI, H2SO4. All right. Arrhenius acids, it's possible that they can ionize more than one hydrogen. That would be a polyprotic acid. Remember, poly means many. Monoprotic acids only ionize one hydronium, only produce one hydrogen ion in solution. Diprotic could make two, so these two hydrogens on sulfuric acid could both dissolve into solution. And then you have triprotic, like phosphoric acid here, that could potentially produce three hydrogen ions in solution. All right, acetic acid, you look back, its formula is HC2H3O2. It's monoprotic. It doesn't lose off for the acetate. The three hydrogens in acetate are not acidic. All right, so Arrhenius Bases defines a base as a compound containing hydroxide that produces OH- ions in solution. So that's going to be all of your ionic bases like sodium hydroxide and potassium hydroxide, calcium hydroxide. All of the metal hydroxides would be Arrhenius bases. Okay, and the alkaline means they form bases when they react with water to make metal hydroxides. That's what this is showing here. All right, so let's see. Acids, easy to identify. They're going to produce hydrogen ions in solution. Bases will produce hydroxide ions in solution. And salts will contain a combination of a metal and a nonmetal, just any ionic compound. And this terminology is typically used with acid-base neutralization reactions. You'll see the acid react with the base. The metal will come from the base. The nonmetal will come from the negative ion of the acid. And then the H and the OH, so the H comes from the acid, the OH comes from the base. Those get together and make water. So that's the neutralization part. And then you have that combination of the metal and the nonmetal left over that produces the salt, which is also known as an ionic compound. All right, let's look at the Bronsted-Lowry definition of acids and bases. At first look, it may not seem much different than Arrhenius, but it is. Okay, so all acids that are Arrhenius acids will also be Bronsted-Lowry acids. It just includes a few more. So, acids are still hydrogen donors. In other words, the acid will donate H plus or H3O plus. By the way, the only difference between those two, well, I'll get into that later. All right, so the acid's going to give away hydrogen ions. That doesn't seem much different. It's not saying it's producing them in solution, though. It's just saying it gives them away to something else. So there doesn't actually have to be water present for the Bronsted-Lowry acid base. Okay, base is a hydrogen acceptor, so it receives hydrogen from something else. Notice that this definition doesn't require the base to have any OH in it at all. And there are quite a few things that are basic that do not necessarily have OH in them or directly produce it in solution. All right, so here's an example of something that falls in that category. So something you would not typically think of as being an acid would be water, and something you would not typically think of, well, it doesn't have OH anyways, it's ammonia. So the ammonia can, when it's put in solution with water, what it does is it receives a hydrogen from a water molecule, and that means that the NH4 is formed, and the OH minus is released into solution that way, but it's not directly like it's coming from the formula from the NH3. So that transfer, there's always going to be two partners in this kind of exchange. So one of them gives away hydrogen, the other receives hydrogen, and that's how in Bronsted-Lowry you identify acids and bases. Okay, so here's another one. the HF transfers a hydrogen to the H2O, and since the HF is giving away hydrogen and the H2O is receiving hydrogen, then that makes the HF an acid and the H2O a base. Right. This does make an acidic solution because once the water receives the hydrogen, then it becomes H3O+, which is going to make the solution itself acidic. All right. The reverse of that reaction could also happen, and in this case the H3O+ would be acting as the acid because it's transferring hydrogen to the F-, which would now, the F- would be acting as a base. So that sets up a condition where when you have a reaction where there's Bronsted-Lowry acids and bases, on the left side of the reaction there will be an acid and there will be a base, and then from that a conjugate base forms because, you know, this thing lost hydrogen. Now it could gain hydrogen, so that would make it behave as a base. And remember, this water gained hydrogen, it was acting as a base. Now it has extra hydrogen, so it could give it away. So if this reaction reversed, then this one and this one would act, this would act as an acid and this would act as a base. So we call these, if they're on the product side, we call them a conjugate acid and a conjugate base. So notice the acid will always be paired up with the conjugate base as far as what's in it, and the base will always be paired up with the conjugate acid. Or another way you could think of it is the conjugate acid is a base that has gained a hydrogen, and the conjugate base is a acid that has lost hydrogen. There's a definition for conjugate acid. There's the definition for conjugate base. Alright, so Bronsted-Lowry theory is needed to explain how things behave as, like NH3 and NaHCO3 behave as bases because they don't have hydroxide in their formulas. Right, so just to make a point here that all Arrhenius acids will behave as Bronsted-Lowry acids or bases as well. But not all Bronsted-Lowry acids or bases would fall in the Arrhenius category. It's a broader definition. Alright, so let's see if you can identify the acid-base, conjugate base for the following reaction. So, give you a moment here. Alright, so looks like the NO3 lost hydrogen and gave it to the OH on the NaOH here. So that would make, oh snap. Okay, that would make the nitric acid the acid, the sodium hydroxide the base, and then the nitrate remaining would be the conjugate base, and the water would be the conjugate acid. Okay, again, give you a moment, give that a try. And let's see. So HCl, the Cl gives away hydrogen to the HCO3. So this is the acid, the HCl. The NaHCO3 is the base. And then afterwards, the HCO3 has gained a hydrogen. That makes this the conjugate acid. The chloride is the conjugate base. Mr. Benner, you're not talking about the sodium. Well, if we actually wrote the net ionic equation here, the sodiums would cancel out, so that's why I'm kind of ignoring them. Okay, so base, acid, conjugate base, conjugate acid. Right, so an amphoteric substance is one that can behave as both an acid or a base in differing circumstances. Water is an example of such a compound, and it helps to be neutral in order to do that. But anyways, And then let's hit the Lewis definition really quickly. So in the Lewis definition of acids and bases, acids accept an electron pair, bases donate an electron pair, so there's not even hydrogen involved here. And I'll do a part 2 of this notes video.